This is the beginning of Chapter 10. You will notice that Chapter 10 has lots of different sections. We are not going to be covering every single section online. You should read through Chapter 10 and be familiar with solids and other kinds of things, but I'm going to be touching on the more traditionally tested kinds of sections from Chapter 10. Chapter 10 is about liquids and solids. And the first section is specifically about intermolecular force. Intermolecular force is a very important concept in chemistry because intermolecular forces give rise to different properties of matter. The first thing we have to do is know the difference between intermolecular force and intramolecular force. So this first section is about intramolecular bonding. Intramolecular bonding, remember, is forces within the molecule. So if we have a molecule and it's covalently bonded, that's the intramolecular force. Molecules are formed by sharing electrons between the atoms. Those are the covalent type I was just talking about. Intermolecular forces are forces that occur between molecules, between neighboring molecules, one molecule and another. For example, some of the intermolecular forces you might be familiar with, dipole-dipole force is an intermolecular force. Hydrogen bonding and London dispersion force. These are the three types of intermolecular forces that covalent molecules can undergo. Intramolecular bonds are stronger than intermolecular forces. In other words, the fact that there is a covalent bond is a stronger bond than, let's say, even hydrogen bonding. So things within the molecule are always stronger than things that are between neighboring molecules. Hydrogen bonding in water. You can notice here on the diagram, you see the water molecule. Oxygen is red and hydrogen is blue. The dots that you see here, and let me get a pen to show you. The dots that you see here represent the hydrogen bond. They are forces between the neighbors. Hydrogen becomes slightly positively charged as a result of the molecular shape. Oxygen becomes slightly negatively charged. So therefore, when a large sample of water, or even greater than one molecule of water is put together, which is in any sample we would get, the neighbors are slightly attracted to each other because there is a positive and a negative attraction. That polarity, the permanent dipole that happens in the water molecule, allows for those things to want to sit next to each other. And there's an added force of attraction or strength there because of this intermolecular force. This comes in Chapter 10, obviously. Earlier than Chapter 10 comes the discussion of shapes of molecules. We will get to that eventually. I know we're going out of order a bit, and some of these discussions have to do with the shape of the molecule. So because we've had it before, I felt that we could handle it now, but usually we talk about it after we talk about molecular shape. But again, we will get back to that. As you can see, it says the blue dotted lines are the intermolecular forces between the water molecules. So let's have a concept check that they say. Which are stronger, intramolecular bonds or intermolecular forces? How do you know? And intramolecular bonds are always stronger because they're forces within a molecule. Forces within a molecule are always stronger than those between. Other kinds of things about intermolecular forces. Phase change. Now, you know a phase change is the changing of a phase from a solid to a liquid to a gas, or vice versa. When a substance changes from a solid to a liquid to a gas, the molecules remain intact. In other words, if I'm heating up some water, I'm not breaking hydrogen from oxygen. H2O stays intact. That proves that the intramolecular force is a stronger force than the intermolecular force, because we can separate from the neighboring water molecules, but we can't separate the water molecule itself. This is the justification that the intermolecular force is weaker than the intramolecular force. The change in state are due to changes in the forces among molecules rather than those within the molecules. Exactly. So here are the three states of matter. I'm sure you're very familiar with pictures like this, but you're saved from my lovely drawing on the chalkboard of these three states of matter. You can see over on the far right we have the solid, regular repeating pattern. We then have the liquid. You notice those molecules are still kind of closely packed, although they're not a regular repeating pattern. And of course, gases, those molecules are free to fill the space of the container. Different phase changes, solid to liquid. What happens there? Energy is added. The motions of the molecules increase, and they eventually achieve a greater movement and disorder characteristic of a liquid. So we do have to overcome some intermolecular force in the solid for those atoms within the molecule to kind of pull apart from the neighboring molecules to have the freedom to move around. Liquid to a gas, again, we have to increase the energy because what happens, as it says here, as more energy is added, the gaseous state is eventually reached with the individual molecules far apart and interacting relatively little. Therefore, they have to have energy to pull away from those attractive forces of the neighbor to maintain that. Densities of the three states of water. Now, of course, water is an exception. Water is actually more dense as a liquid, and you can see that as a liquid, water has a density of a 0.9971. As a solid, it's actually slightly less, and that has to do with the open structure of water. The water molecule, when it is put together, has kind of an opening in the center, and you can see I actually have a kit that we'll look at that we'll put together and build kind of a water molecule structure. And we will see that there is a larger volume that is occupied by the same number of molecules. Therefore, the density decreases. So that's why you see the density of water in a solid is actually less than that of a liquid. That is the only substance for which this is true, and that's an unusual situation. Of course, a gas, least dense. That's true for all phases of any substance. The gas phase is the least dense. So let's look at the intermolecular forces a little bit more. Now, this particular PowerPoint by this textbook company we're using talks about dipole-dipole forces first. Probably would not have. I usually like to talk about the weakest, then the middle, then the strongest. The weakest is the London dispersion, and then the dipole-dipole force, and then the hydrogen bond. But this book is putting dipole-dipole forces because they're probably going to put dipole-dipole and hydrogen bonding in a similar category. And let's see. All right, what are they talking about here? Dipole moment. It's kind of a funny word, but essentially what it means is molecules that are polar have a positive and a negative end to them because of the arrangement of the electrons. Again, we'll get back to that in another chapter. So therefore, one part of the molecule is positive and one is negative, and that sets up a dipole. Two poles. You know, di means two. So two poles, a positive charge and a negative charge. And sometimes we say that molecule has a dipole moment. So molecules with polar bonds have this electric field as if they had a center of positive charge and a center of negative charge. They can then attract the neighbor. So if one center of positive charge is near another molecule, it can attract a negative end of the neighbor. Molecules with a dipole moment can attract each other electrostatically. They line up so that the positive and negative ends are close to each other. And that positive and negative that we see and saw in the picture of the water molecule earlier with the blue dots was an example of the neighborly attraction. About 1% as strong as covalent or ionic bonds. So you can see that the intermolecular force is much weaker than the intramolecular. It does add some strength to the molecule, but that's not the only thing that's there. Hydrogen bonding. Well, hydrogen bonding is a dipole-dipole force and involves a polar molecule, but a very special one. It's hydrogen bonded to nitrogen, oxygen, and fluorine only, because those three elements are highly electronegative. Those atoms are highly electronegative, and therefore the electrostatic charge, the positive and negative charge that's set up there, is extreme. The hydrogen is extremely positive, and the nitrogen, oxygen, or fluorine is extremely negative, and thus it's an exaggerated dipole-dipole force, but we actually call it hydrogen bonding. And then the last intermolecular force is called a London dispersion force. Sometimes you'll see it just as dispersion force. This happens between all molecules. And what it is you can see here, an instantaneous dipole that occurs accidentally in a given atom. It induces a similar dipole in a neighboring atom. Those electrons in an atom try to be as far apart as possible, but there might be, as it says here, accidentally, as these electrons are moving around, a time when extra electrons, some of the electrons, there are more electrons on one side of the molecule than the other. At that brief moment, if there are extra electrons on the right-hand side, let's say, what ends up happening is there is a negative charge on that side. So let's say we have argon. Now argon is an element, and I'm going to draw a electron cloud. That's going to be my electron cloud. Now, in a perfect situation, argon would be perfectly round. But sometimes, as those electrons, and argon has, let's see, 18 electrons. So its 18 electrons are kind of around there somewhere in certain regions of space. There might be a situation where, like in this picture, maybe some of those electrons moving around are more on the right-hand side. So what's going to happen? Well, that means argon next to another argon, these electrons are going to move over here because they're going to want to get away from these electrons over here. So what's going to happen is, in a sample of argon gas, when one atom's electrons become misaligned accidentally, it's going to influence the neighbor, which is going to influence its neighbor, and its neighbor, and its neighbor, and eventually the entire sample is going to kind of shift as a result. It's like being in a big crowd of people, and somebody bumps somebody, and one person moves, and suddenly everybody kind of gets jostled around a bit, because you're doing that in response to kind of being bumped on one side, and you bump somebody else by mistake, and they bump somebody and the next person, and so forth. It's kind of a domino effect. So that's what a London dispersion force is. It's a temporary, brief situation where a nonpolar molecule becomes sort of polarized. It's significant in large atoms and molecules because in a huge atom or molecule, or a large sample, you have lots of electrons, and those electrons have a higher chance of becoming misaligned, and thus creating a dispersion force. Remember, it occurs in all molecules, including nonpolar ones. So in like this argon example, argon is a gas, and it really has very little interaction with its neighbor. It does not have a very high intermolecular force, but it does have a London dispersion force. What do melting and boiling points have to do with intermolecular force? In general, the stronger the intermolecular force, the higher the melting and the boiling points. And as you can see here, if we look at the boiling points of the covalent hydrides of the elements in groups 4, 5, 6, and 7a, that means if we have hydrogen bonded to different elements, you can see them all here. In period number 5, all the way over here on the right, we have hydrogen bonded to tellurium, hydrogen bonded to tin, hydrogen and iodine, and tin and hydrogen, or hydrogen bonded to tin. Did I say tin here? I think I meant antimony. Sorry about that. In any case, you can see where that falls. And you can see that where tellurium is, and you can see where tin is, and so forth. And in general, you notice these red ones, they're going like that. Tellurium, selenium, sulfur, and oxygen are in the same family. So the red ones are all in one family. The orange ones are all in one family. The green ones are in one family. And then the blue ones are in one family. I think I mentioned that hydrogen bonding is between hydrogen and oxygen, fluorine, and nitrogen. You notice those are the three right here. They are the highest boiling point in its family because those hydrogen bonds give an added strength to those molecules, and thus it takes more energy for those molecules to change phase from the liquid to the gas. So in these intermolecular forces do give rise to some different property changes. So which molecule is capable of forming stronger intermolecular forces? We have N2 and H2O. And hopefully you know that the answer is, and it says explain, H2O. We know that H2O is a polar molecule. And if we forget that, we'll certainly go back and look at that in another chapter. Nitrogen, N2, is a nonpolar molecule, so it would have a dispersion force. Let's see what they have to say, if anything. Maybe they don't. Nope, they didn't, but that's the answer. Liquids. Remember, liquids are substances that have low compressibility, they're not rigid, and they're highly dense compared with gases. They do have surface tension. That means they kind of form a skin over the top. It's kind of an added strength. And molecules that have hydrogen bonding, like water, will be substances that can hold on to their shape better. Liquids with large intermolecular forces tend to have high surface tensions. That's why you can float things on top of the surface of water. You know, you can take little pieces of paper and things like that, and they will float on the surface of water. Or a needle, something like that, or a paper clip. You can actually float those on for a bit of time. That ends our section for this.